In this module, you will learn about the control peripherals, which include the analog to digital converter, EPWM, eCapture, and EQEP. The ADC module is based around a 12-bit converter. There are 16 input channels and 16 result registers. The SoC configuration registers select the trigger source, channel to convert, and the acquisition prescale window size. The triggers include software by selecting a bit, CPU timers 0, 1, and 2, EPWM A and B 1 through 8, and an external pin. Additionally, ADC in 1 and 2 can be fed back for continuous conversions. The ADC module can operate in sequential sampling mode or simultaneous sampling mode. In simultaneous sampling mode, the channel selected on the A multiplexer will be the same channel on the B multiplexer. The ADC interrupt logic can generate up to 9 interrupts. The results for SoC 0 through 15 will appear in result registers 0 through 15. The top example on this slide shows channels A2, B3, and A7 being converted with a trigger from EPWM1 SoCB. After A7 is converted, ADC in 1 is generated. The bottom example extends this with channels A0, B0, and A5 being converted initially with a software trigger. After A5 is converted, ADC in 2 is generated, which is fed back as a trigger to start the process again. The example on this slide shows channels 0 through 7 being converted in simultaneous sampling mode, triggered initially by software. After channel 3 is converted, ADC in 1 is generated. After channel 7 is converted, ADC in 2 is generated and fed back to start the process again. ADC in 1 and ADC in 2 are being used as ping-pong interrupts. This device has 3 analog comparators that share the input pins with the analog to digital converter module. If neither the ADC or comparator input pins are needed, the input pins can be used as analog I/O pins. As you can see, one of the inputs to the comparator comes directly from the input pin, and the other input can be taken from the input pin or the 10-bit digital to analog converter. The output of the comparator is fed into the EPWM digital compare submodule. This slide is a brief overview of a few of the ADC control registers. It can be used as a reference during the lab exercise. Pulse width modulation, or PWM, is a technique used to represent a signal as a sequence of pulses. A PWM waveform has a fixed carrier frequency, fixed pulse amplitude, and the pulse width is proportional to the instantaneous signal amplitude. Power switching devices are difficult to control in the proportional region, but are easy to control in the saturation and cutoff region. Since PWM is a digital signal and easy for microcontrollers to generate, it is ideal for use with power switching devices. An EPWM module can be synchronized with adjacent EPWM modules. The generated PWM waveforms are available as outputs on the GPIO pins. Additionally, the EPWM module can generate ADC starter conversion signals and generate interrupts to the PI block. External trip zone signals can trip the output and generate interrupts too. The output of the comparators are used as inputs to the digital compare submodule. Next, we will look at the internal details of the EPWM module. The EPWM, or Enhanced PWM Block Diagram, consists of a series of submodules. In this section, we will learn about the operation and details of each submodule. In the time-based submodule, the clock prescaler divides down the device core system clock and clocks the 16-bit time-based counter. The time-based counter is used to generate asymmetrical and symmetrical waveforms using 3 different count modes: count up mode, count down mode, and count up and down mode. A period register is used to control the maximum count value. Additionally, the time-based counter has the capability to be synchronized and phase shifted with other EPWM units. The upper two figures show the time-based counter in the count up mode and count down mode. These modes are used to generate asymmetrical waveforms. The lower figure shows the time-based counter in the count up and down mode. This mode is used to generate symmetrical waveforms. If needed, an EPWM module can be synchronized with adjacent EPWM modules. Synchronization is based on a sync-in signal, time-based counter equals 0, or time-based counter equals compare B register. Additionally, the waveform can be phase shifted. The compare submodule uses two compare registers to detect time-based count matches. These compare match events are fed into the action qualifier submodule. Notice that the output of this block feeds two signals into the action qualifier. The figures here show the compare matches that are fed into the action qualifier. Notice that with the count up and count down mode, there are matches on the up count and down count. The action qualifier submodule uses the inputs from the compare logic and time-based counter to generate various actions on the output pins. These first few modules are the main components used to generate a basic PWM waveform. This table shows the various action qualifier compare match options for when the time-based counter equals 0, compare A match, compare B match, and period match. Based on the selected match option, the output pins can be configured to do nothing, clear low, set high, or toggle. Also, the output pins can be forced to any action using software. The next few figures show how the action qualifier uses the compare matches to modulate the output pins. Notice that the output pins for EPWM-A and EPWM-B are completely independent. Here, on the EPWM-A output, the waveform will be set high on 0 match and clear low on compare A match. On the EPWM-B output, the waveform will be set high on 0 match and clear low on compare B match. This figure has the EPWM-A output set high on compare A match and clear low on compare B match, while the EPWM-B output is configured to toggle on 0 match. Here you can see that we can have different output actions on the up count and down count using a single compare register. So, for the EPWM-A and EPWM-B outputs, we are setting high on the compare A and B up count matches and clearing low on the compare A and B down count matches. And finally, again using different output actions on the up count and down count, we have the EPWM-A output set high on the compare A up count match and clear low on the compare B down count match. The EPWM-B output will clear low on 0 match and set high on period match. The deadband submodule provides a means to delay the switching of a gate signal, thereby allowing time for gates to turn off and preventing a short circuit. To explain further, power switching devices turn on faster than they shut off. This issue would momentarily provide a path from supply rail to ground, giving us a short circuit. The deadband submodule alleviates this issue. The PWM chopper submodule uses a high-frequency carrier signal to modulate the PWM waveform. This is used with pulse transformer-based gate drives to control power switching elements. As you can see in this figure, a high-frequency carrier signal is ANDed with the EPWM outputs. Also, this circuit provides an option to include a larger one-shot pulse width before the sustaining pulses. The trip zone and digital compare submodules provide a protection mechanism to protect the output pins from abnormalities such as overvoltage, overcurrent, and excessive temperature rise. The inputs to the digital compare module are the trip zone pins and the analog comparator outputs. This module generates compare events that can generate a PWM sync, generate an ADC starter conversion, trip a PWM output, and generate a trip interrupt. Optional blanking can be used to temporarily disable the compare action in alignment with PWM switching to eliminate noise effects. The PWM trip zone has a fast, clock-independent logic path to the PWM output pins, where the outputs can be forced to high impedance. Two actions are supported: one-shot trip for major short circuits or overcurrent conditions, and cycle-by-cycle trip for current limiting operation. The event trigger submodule is used to provide a triggering signal for interrupts and the starter conversion for the ADC. Event trigger interrupts and starter conversions can be generated on counter equals 0, counter equal period, counter equals 0 or period, counter up equal compare A, counter down equal compare A, counter up equal compare B, counter down equal compare B. Notice counter up and down are independent and separate. The high-resolution PWM feature significantly increases the resolution of conventionally derived digital PWM. High-res PWM divides a clock cycle into smaller steps called microsteps. The step size is approximately 150 picoseconds. This is typically used when PWM resolution falls below approximately 9 or 10 bits, which occurs at frequencies greater than approximately 160 kHz with a system clock of 80 MHz. This slide is a brief overview of the EPWM control registers. It can be used as a reference during the lab exercise. The capture module allows time-based logging on external signal transitions on the capture input pins. The capture module features a 32-bit timestamp counter to minimize rollover. Each module has 4 capture registers. Polarity can be set to trigger on rising or falling edge, and trigger events can be pre-scaled. The capture module can operate in absolute timestamp mode or difference mode, where the counter resets on each capture. If the capture module is not used, it can be configured as an asynchronous PWM module. The QEP circuit decodes and counts the quadrature encoded input pulses. This circuit can be used to interface with an optical encoder to get position and speed information from a rotating machine. Using a quadrature decoder state machine, we can determine if the counter is incrementing or decrementing, and therefore know if the disk is moving clockwise or counterclockwise. The QEP module features a direct interface to encoders. In addition to channels A and B being used for rotation directional information, the index can be used to determine rotational speed, and the strobe can be used for position from a homing signal. In this lab exercise, a 2 kHz 25% duty cycle PWM waveform will be generated by EPWM1. The waveform will be fed into ADC channel A0 using the jumper wire. The ADC is being triggered by EPWM2 at a rate of 50 kHz. After each conversion, the CPU will copy the results into a circular buffer. Using Code Composer Studio, we will view the waveform in the time domain and frequency domain. Additionally, we will experiment with the real-time emulation features. You can pause this presentation now and try this lab on your own, or you can watch me do the lab exercise. A project named Lab 3 has been created for this lab exercise. We'll open the project by clicking on Project, Import Existing Project, and then navigating to the project under Lab 3 Project, clicking OK, and Finish. Notice the project is listed under the Project Explorer window with its files. Before we start, we'll take a look at a few of these files. First, we'll notice that in GPIO.c, GPIO0 is set for a 1, which gives us EPWM1A as an output on that pin. Next thing we'll take a look at is the EPWM.c file. And in the top portion of this file here, we are using EPWM2 to trigger the ADC at a 50 kHz rate. And then down below here, EPWM1 is being configured to generate a 2 kilohertz symmetrical PWM waveform. And we are setting the values up for the timer period and the duty cycle right over here in the middle. And these values are being defined in lab.h, and if we look into the lab.h file, we'll find those values being defined under the constant definitions. One other thing we want to take a look at is the ADC, as we know, is going to be sampling the PWM waveform, and inside of the ISR, when we take a look at the ADC, which is located right here at 1.1, we're setting up a circular buffer, and we're going to then plot the circular buffer out with the Code Composer Studio. You'll also notice that in the bottom here we are toggling GPIO 34 half a second rate on off with this piece of code right here, and with the GPB toggle instruction. So we're going to toggle that pin that is connected to the LED. This will serve as a visual indicator that we're getting in and out of the ISR, number one, and number two, we will then again use this in the flash lab as proof that we actually flashed the device. So at this point here, that's pretty much the main pieces of code. We've taken a look at the ISR. We understand now where the constant definitions are being used in EPWM.C file, and setting up the EPWM module itself. And I guess we'll take a look at the ADC.C file as well. Here we're setting up the ADC, and down here we're taking care of enabling it for interrupts. We saw 1.1. Here's the 1.1 piece right here, and it's coming off of core interrupt line 1 as well. And we understand now the GPIO pin is now configured, so we have an output coming out on that pin for EPWM1A. Next, what we'll do is we're going to build it. First, build it, making sure everything builds properly and we don't have any problems in the problem window. And then what we'll do is we will click the debug button. That will change us over to the debug perspective and loading the program. Please remember that if the device has been power cycled since the last lab exercise, be sure to configure the boot mode to emu_boot_SARAM using the script menu, which is right over here, in case you have power cycled it. Okay. What we'll do now is we're going to take a look in our memory browser. We'll take a look at the contents of the ADC result buffer, and we'll set that up with the address of, and it's ADC buff, and the addresses and labels are case sensitive. And we'll go and we'll take a look, and we'll basically see we don't really have too much right now in this ADC buffer. The next thing what we'll do is we are connecting the jumper wire in the kit between EPWM1A, which is pin 17 on the header, to ADC in A0, which is pin 3. Okay, the pin assignments for this control stick can be found in the last page of this lab exercise in the workshop manual. So right now I've got those wires connected between pin 17 and pin 3. And what we'll do now is we will run the code for a few seconds and stop it and see if the memory browser updates. So we run it, and now we'll stop it, and sure enough it did update, and you can see the updates there. And pretty much what we're expecting to see, 2 kilohertz PWM waveform. As we can see, we have a bunch of zeros and then pretty close to F values in between. And what we'll do now is we'll open up a graph window. So under Tools, we'll click on Graph and a single time graph, and we'll set that up to an acquisition buffer size of 50. The data type will be set to 16-bit unsigned right over here. The sampling rate will be set to 50,000. The address, start address, will be ADC buff. Once again, case sensitive. We'll set the display data size to 50. And then we'll set the time display unit to microseconds. And we'll click OK. And sure enough, right now we have a graph on the side representing the 2 kilohertz PWM waveform. What we'll do is we'll measure this waveform. So we've generated a 2 kilohertz 25% duty cycle symmetrical PWM waveform. The period of 2 kilohertz is 500 microseconds. So let's confirm this with the measurement marker mode. So what I'll do is I'll click on the measurement marker mode and take my first point of the waveform right here. And then I'll do it again with the measurement marker mode and take my second point right over here. And you'll notice the difference between the 2 points, x2 minus x1 equals 500. So we measured that, and I can clear my measurement marker mode just by right-clicking and say remove all measurement marks. Okay, the next thing we'll do is we'll take a look at the frequency domain. So Code Composer Studio also has the ability to make frequency domain plots, and it does this by using the PC to perform a fast Fourier transform in the data. So let's go under Tools, and we'll take Graph, and this time we'll take FFT magnitude. The acquisition buffer size will be set to 50. We'll set the data sample size, data sample type to 16-bit unsigned. We'll set the sampling frequency over here, the sampling rate, to be 50 kilohertz. And then once again we have the start address, case sensitive again, ADC buff. We will select the plot style to be bar, and I'll take a FFT order of 10. And we'll take a look at that, and sure enough, here is our frequency domain plot, and I can just left click and hold the mouse down, and we'll notice that the peak here it's the bottom number that I'm reading right down there. This is the top one you see is the amplitude, but if you look at the lower bottom piece, it's at about 2 kilohertz is what I'm reading right here. So that's our frequency domain plot. Next thing we'll take a look at will be using the real-time emulation features. So let's switch back to our single-time graph window. And this real-time emulation is a special emulation feature that allows the windows within Code Composer Studio to be updated at a rate up to 10 Hertz while the MCU is running. And this not only allows the graphs, but all the windows, the watch windows, the memory browser windows, to be updated as well. And it allows the user to make changes in the watch windows and see how those changes affect the MCU behavior, or the processor behavior itself. So right now we have the single time window displayed. The next thing I'm going to do is I am going to enable that for continuous refresh by clicking on this button right here, Enable Continuous Refresh. And if I'd like, I can also go to the memory window and do the same here and set that one up for continuous refresh. Let's go back to the single time. And what I'm going to do this time now is run the code, but we're going to run it in real-time mode. And by doing that, you'd click on Scripts, Real-Time Emulation Control, Run Real-Time with Reset. And right now we're running in real-time mode, and if you notice right down here, the values are changing. And what I'm going to do is I'm going to very carefully pull the wire out of the ADC and watch how the graph changes. And sure enough, I just pulled the wire out, And now when I plug the wire back in, the graph's back there. Once again, I pull it out, graph flattens out, and if I push it back in, we have the graph back. Likewise here, I can view the memory window, and I can see the values are changing slightly there. If I pull the wire out, they're all changing. Plug the wire back in. So I have both windows being updated in real time. Okay, next what we're going to do is we are going to fully halt the processor in real-time mode, and you do scripts, full halt under real-time emulation control. And at this point here, what we will do is we will terminate the debug session and close the project.